For our system design, there were a few different items we had to meet and a few we really like to have to make the design a lot easier. Um, just to meet the base requirements, we had to have fairly low latency, ideally under 100 milliseconds, but somewhere around that ballpark. It had to be high accuracy, classifying the majority of the items correctly, ideally looking for somewhere close to the 70 to 80% range. Had to be able to use it with LIDAR and had to be compatible for us. Um, but then we also were looking for something that ideally we could use out of the box, didn't have to implement from a paper, that would run fairly natively with Python, and if possible, we get some automatic bounding boxes with. After reviewing a number of different papers, we found that SPV-NOS actually works really well with this, and Jorge will explain why that is a little bit later.
During the creation of our project, we designed several different models before coming to our final version. Our initial design had 5 nodes, which each published and subscribed to topics to communicate data. The LIDAR node was responsible for reading in LIDAR point cloud data. The dataset reduction node then downsampled this data in order to reduce computational complexity. The SPV-NOS node was responsible for segmenting and classifying this reduced dataset, and the post-processing node used the classified data to create bounding boxes. Finally, the terminal node was responsible for displaying information about the process like latency and frame data to the user. We later made modifications to this design by adding service-client communication between nodes so that slower, computationally intensive nodes like the SPV-NOS and post-processing nodes would request data on a by-demand basis. Our final version streamlined the initial process by combining the functionality of the initial LIDAR and pre-processing nodes, as well as combining the SPV-NOS and post-processing nodes into the model node. The terminal node was also repurposed as the visualizer node, which presented the process point cloud and bounding box data as a series of images which could be understood by the user.
To choose a segmentation and classification architecture, we came across several approaches that worked really well. The two best ones we found were DryNet++, as well as SPV-Conv, which produces the SPV-NOS that we've been discussing this whole semester. For us, what made us go with SPV-NOS was these two major things that really stood out to us, and it's this large computation reduction and this high measure speed up over the Minkowski net algorithm, while maintaining a higher accuracy than most architectures that are out today. The benefit being that, it achieved all this by first voxelizing and then performing sparse convolution and then devoxelizing. This algorithm was even better in that it can work on both CPU and GPU and even perform faster with more GPUs available.
We decided that to make bounding boxes, we would take the point cloud data and the classifications given to us from SPV-NOS and filter out the classes that weren't important, separate the classes into their own array, and remove points too close to the car. Once that was done, we would run the Birch clustering algorithm on each class of points, and for each cluster that Birch made, we would put a bounding box around it. Looking more into the challenges faced, originally our algorithm was designed to utilize dbScan. However, dbScan was slow and inconsistent, so we had to search for a different clustering algorithm. We tried optics and Birch. We found that optics, while more consistent, was slower on average than dbScan. However, lucky for us, we found that Birch was not only faster, but significantly more consistent than dbScan.
So from the recording of the visualizer, we can see the car approaching the AutoDrive car with a bounding box around it. And if we scroll further ahead, we can see multiple cars in a parallel parking and parking situation around the car. This is all from a top-down view, but as the visualizer only makes them in a top-down view, but we have pictures of different angles. So we have this picture, which is of the parallel parking, and it outlines both the cars and other objects on the road. And along with that is this scene where we can see the cars going one way, and across the median you can see a bus and other cars.